Today, let us start off with kinematics. The three parts to kinematics. First is about the formula. Then we'll go on to look at ST, VT, and AT graph. And finally, we'll look at trajectory. Let us kick off with the first part first. There is a total of 4 sets of formulae that you can use for kinematics. The first set comes from the definition of acceleration, where acceleration is defined as the rate of change of velocity. So it's v minus u. V is always the final velocity, u the initial. The second set, you'll be using the definition on average speed. In the calculations for average speed, we can have the final speed add up with the initial speed divided by 2, which is equal to the total distance traveled divided by the time taken. With these two sets of formula, if you were to remove the v, in this case, we substitute the v with u plus at, which is what we have down here, then you will end up with the third set of formula, s equal to ut plus half at squared. Don't have to memorize that. That set of formula is in the data booklet. Using the same equation 1 and 2, we could now try and get rid of t by dividing this expression with this and this with this. And your t will cancel away. So you end up with v squared equal to u squared plus 2as. So that is actually the 4 set of formula that you can use for your calculations on kinematics. With that, we move on now to the ST, VT, and AT graph. A very simple illustration is to actually have a ball that you throw upwards, and the ball will go right up to the top before it returns back. All right, we'll not be discussing about frictional force for now, and it is pivotal that you need to actually have a convention. So we're going to work out both convention. So in this question itself, let us assume, all right, the assumption rather, based on this graph, is obviously when the object is moving upwards, that means the convention is upward is positive. All right. So that's the reason why the speed at this point is here. So assuming it is 1 meter per second. Okay, so it's moving upwards. All right. The ball will be subjected to acceleration due to gravity, which is constant. So in this case, we expect the acceleration to be negative. And therefore, because of that, if you can recall back in your O level, the gradient of a VT graph is the acceleration. So this is a quick recap. Gradient of VT graph is the acceleration. Okay. So so in this case, you will notice that the gradient will be negative. All right. And in this case, specifically negative 9.81, since the acceleration is equal to minus g. All right. And certainly at this point down here, you expect the speed to go to 0. And then after that, you will then move down at point C. His speed will be minus 1 meter per second. Negative 1 because in this case, the velocity of the ball will be acting downwards. Okay, if we're now using the VT graph, we can now translate that into the AT graph. All right. So as we said, the gradient is the acceleration. So therefore, because of that, we can see that in this case, the value of A is constantly at minus g. Okay, now we take a look at the displacement time graph. To do the displacement time graph, another thing to recap that in O level that you need to know on the VT graph, the area under the graph is actually the displacement. Okay, so in this case, the area under the graph, as you can see, as you move further up, this area is in actual fact the height. And what's more important is that if you will calculate the area, it will actually be positive. All right. Say assuming if this is actually 1 meter per second, the gradient is 9.81. We could in actual fact let this be t naught. So in terms of the gradient, minus 1 divided by t, which will be equal to minus 9.81. And so in this case, your t will be 0.1 second. Okay. So the displacement or the area under the graph, and therefore the height of here would actually in actual fact be half times 1 times 0.1, and that we will get 0.05 meter Okay, so in this area here, this is 0.05, so it's positive in value. All right, and if we were to calculate for this, we need to note that this one now, because the you will find that the area below the x-axis, so the area under the graph will now be negative, and hence because of that, if you were to sum up the displacement and this, both the displacement to add up together, all right, for point A to point C, it will be 0. When you obviously when the ball starts off at point A, the displacement is 0 as well. And you will find that this is actually the ST graph. How you derive the ST graph from the VT graph is by looking at the fact that the area is actually equal to the displacement. And more importantly, the gradient of the ST graph is actually the velocity. So the velocity is very high at this point. So displacement starts at 0. So the gradient to be very steep. By this point, the gradient is absolutely 0 because the velocity is 0. And at this point down here, it's important to note that the velocity is negative. Therefore, the gradient of the ST graph has to turn negative. So bear in mind that initially the gradient is positive, then on this portion it becomes negative. And obviously it returns back to 0, as we mentioned, that both the areas, when they add up together, because this is positive, this is negative, it will give you end up with actually a 0 displacement. Okay, let's now take a look how the formula helps us to explain the graph. If you look at the VT graph, we can use equation 1, all right, the first set of formula from the definitions of acceleration. And if v equal to u plus at, you know a is minus g. This will be v equal to u minus gt. So your v is your y, your t is your x. So your gradient is negative g, as explained. For the ST graph, we can explain by using formula set 3, s equal to ut plus half at squared. Similarly, your a is the minus g, so we can substitute that. So if we want s to be 0, all right, of course, we can manipulate this information. If s is 0, then your t could be 0, or your t could be at this time. And it's actually a parabolic in shape. There's actually one more graph that sometimes could be asked in exam, which is the VS graph. If they want the VS graph, then you have to use formula set 4, the last set of formula, v squared equal to u squared plus 2as. So this will be the expression now. And remember that your graph now looks somewhat like y squared equal to k minus kx, because your 2g is constant, all right? And your u squared is actually a fixed value. So if we were to substitute and make s or your x as 0, then your v is plus minus u, which is the reason why when s is 0, you have two possible values, because one is going up and one is coming down. Then the other one, finally, when y is 0, which means that your velocity is 0 right at the top. Then in this case itself, your displacement is this. So this formula that you have down here is in actual fact your height actually, all right? The final graph that we want to talk about is to distinguish the difference between displacement time graph and distance time graph. As you probably will have recalled, for distance, it is a scalar, and therefore it just aggregate or sum up the magnitude of the displacement. So in this case, it will not recognize that when it is coming downwards, it will not recognize that those values are negative. They will still just take the magnitude as being a positive value. So you can see that at this point, the gradient is still 0 because gradient of the distant time graph is the speed. So the speed here is 0. Then subsequently, the gradient will be steep because the speed of the ball is actually increasing when it falls back to point C. Okay, let's now take a look at what happens if we decide to use a convention where downward is positive. I think the first thing to recognize is that the acceleration will now be plus g. Therefore, in terms of the VT graph, it will be a positive gradient. And initially, when the ball is actually moving upwards, the speed will now become negative instead of positive. So the green line is for the convention when downward is positive. In terms of the displacement, it is up to us to set the datum where the displacement is 0. So the purpose of this discussion, we're going to set displacement to be 0 for the ball right at the top. In that case, if right at the top, the displacement is 0, then we know that that is the time when the ball actually is temporarily at rest, which is at this point. So you can see that the displacement is labeled as 0 here. And this graph we have actually went the other way around, because at the point of position A and C, all right, the displacement would have been S, right, since downward is positive. Similarly, when you look at the velocity displacement graph, all right, you can see that the again, when the displacement is 0, all right, the speed is 0. But when the displacement is at this point here, S, then there's two possible speed, because it can actually be upward, which is negative, and it can be downward when it's positive. Okay, how if we decide to change the datum for the displacement? So let us say that we change that now, we change it, we want the displacement to be 0 at position A and C. In the case, there's literally no change to the VT graph, it will still be the green line, all right? As far as for the displacement graph is concerned now, there will be a change, because instead of, when you start off with position A must now be at 0 displacement, C must also be 0. When it is right at the top now, it will be a negative displacement with the maximum value, so as you can see down here. So the dotted line becomes the new displacement time graph when the datum here is 0. For the VS graph, you will find that if the datum has now shifted to A and C being 0, in the same way, when the ball first starts, the 0 could be plus and minus. So this graph will have to be shifted in this direction. So you probably can see here. Okay. The reason is because that the S initially is 0, isn't it? So when at position 0, you could have been going upwards, which is negative at this point here for A. Then at point C, it's actually right at the top, because it's coming back down, and downward is positive. So this will be here. Right at the highest point, where is your minus S, that is where the speed is 0. Now let us take a look at the same example of the ball moving up and down, but now with frictional force. So when the ball is actually moving up, it will face two forces, all right, acting on it. One of it is obviously its weight. The second one is the frictional force, or the air resistance, which actually has a formula, which is that resistance force is equal to kV, and K is actually a dimensional constant or proportionality constant. So by working out the acceleration, it will be minus G minus Km over V. And now if you take a look at it when the ball is moving from B to C, you'll find the direction of the kV will have changed, because the ball is now moving downwards. So the resistance force is upwards. So based on that, the difference is that the acceleration will end up as minus G plus Km over V. This is very important, because it simply just means that the magnitude of the acceleration is maximum when the ball is at point A, because your V, or your speed, is actually maximum at this point. But as it's moving up, the speed will start dropping, so this value will drop. So the magnitude of your acceleration will start decreasing until at this point down here, where your speed is 0, it will just merely be G. And moving downwards here, you can see that because it's a positive component now, all right? And hence, because of this, you'll find the magnitude of acceleration will start to get smaller than G. So to sum up, the acceleration, the magnitude of the acceleration from point A is larger than G here. As you move further up, you go to G. As you come further down, you'll be less than G. So how that translates for the graph is that if we obviously still take convention as upward as positive, then your speed could start off as here, which means the gradient is actually negative, obviously, but more importantly, it's actually the steepest, as we mentioned. So as you reach at this point down here, the gradient of the tangent at this point must actually be negative G, and you can see that the gradient get less steep as you move forward here. So to mirror the point ABC, it will actually be A, this will be point B, and this will actually be your point C, all right? To correspond to the motion of the object. You can see that I've also indicated the dotted line. The dotted line is indicated based on the earlier graph that we have plotted, which means there's no air resistance. If there's air resistance, certainly will travel along the red line. And you probably got to tell that it will take actually a shorter time for the ball to reach to point B with friction, which is logical because now some of the energies need to be translated, all right, to work done against non-conservative forces like a frictional force or the air resistance. And the final point is that to take note that it means the time it takes for the ball to move up and for the ball to come back down, all right, would actually be different because the area under this graph and the area under this graph must actually end up as equal because this is where the height that you move up, and when from B to C, this is where indicates the displacement for it to move back B to C. So the two areas, if add up together, and remember this area here is negative, should actually end up as 0 as well. So if the two areas are equal, and as you can see that we expected the speed that you move initially up to be U, okay? So when the speed that comes back down, we let it be V. As we mentioned, the speed here, when it comes back down, will be smaller than U, due to the fact that we mentioned that the energy will now have to be translated to work done against air resistance. So hence to conclude, the magnitude of V when the ball reaches back to point C must be less than the U, all right, which is the initial speed. And the time it takes for the ball to move up will be shorter than the time it takes for the ball to come back down.